James Gregory was a very, very prominent mathematician of the 1600s. You'll notice that he came right before Isaac Newton really found his prominence. So he was kind of like the cutting edge of calculus and its development. He was an astronomer, and he's probably most famously known for making this telescope right here. But he's kind of got a tragic life, so let's get into what he did. He was born in Aberdeen, Scotland, and he later worked in London and St. Andrews. He, like I said, he worked in the early stages of calculus. It was just a few decades before Newton and Leibniz really made their prolific discoveries and, well, groundbreaking discoveries. He worked with infinite series and as well as geometry. In fact, he was a huge bridge between geometry and the new budding calculus. He was a lot of the brains behind that. He had to use a lot of his geometry or just geometry in general, to create this Gregorian telescope, which he's very well known for. He developed early ideas of infinite series and quadrature, which is just a fancy word for area. That's what they called it back in the day. He was very, very brilliant, but also very quiet. He was very often by himself in his own sort of cubicle of isolation. But his specific contribution to this week's lectures is he played a crucial role, again, in geometry and in developing geometry into the analysis / calculus that we know today. But he also studied problems involving the area under the curve, which is something that is what an integral is. And he, like I said, he came before Isaac Newton. So he's part of that sort of developing story. And as we know, the integral is defined in terms of an infinite series, really. And he also was a proponent of, or he was a discoverer of early infinite series representations that allowed mathematicians to compute these areas more sort of systematically, if you will. His work with inverse trigonometric functions, specifically the arctangent. In fact, he found in a series representation for pi itself, and it's actually not too hard to do. I could probably do it right quick. Yeah, let's just go ahead and see kind of what Gregory did to develop a series representation of pi. I think we have the tools. We'll go right back to Gregory here in a second. But let's see kind of his idea. It all comes from this basic idea of the infinite geometric series. So it was known at the time, this really has roots back to ancient Greece and Euclid, or at least it started there. But we had to deal with infinity, and we needed these brave mathematicians who were willing to deal with infinity, like Gregory, to come up with these formulas for infinite series. But this is what we call the geometric series. And we know that this ratio right here is precisely equal to 1 plus x squared plus x cubed plus x to the fourth plus, you can hopefully guess what's going to happen next, as long as this ratio holds, as long as x, or I should say the absolute value of x, well, I'll write it like this. X is wedged between these two values, inclusive. So this is our series representation for this geometric series. But what Gregory did, the essence of what he did, is he just started wondering, well, what would happen if I replaced this x here? If this is true for all x values that satisfy this condition right here, then what I could do is replace this x value with, how about just negative x squared? So let's see how that would change things. Oops. That's supposed to be an equal sign. So again, what Gregory did is he replaced this with negative x squared. We're going to need our differential calculus skills here in a second. Okay, so all of the x's got replaced with negative x squared. Again, that's because this is true as long as this condition holds. Well, let's just see how things simplify. I think this implies that 1 over 1 plus x squared is equal to 1 minus x squared plus x to the fourth minus x to the sixth plus x to the eighth. I'm making sure I'm getting this right. Looks like we're picking up even numbers. So the next one's minus x to the 10th plus ... And that will continue. All right, but what Gregory then did, again, he didn't do this directly because he didn't have the tools of calculus yet. But now that we're at this stage, we just have to wait another 50 years until this guy named Isaac Newton developed the ideas we're about to use. What we could do is anti-differentiate both sides of this equation with respect to x. And what will we create? Well, we'll create this new series. Checking this out right here, we know a function whose derivative is 1 over 1 plus x squared. That is, of course, the arctangent. And this is equal to, and I'll include my constant of integration right here, the arctangent plus some constant c. Of course, if you anti-differentiate both sides, you're picking up a family of functions, not just one functions, because the derivative of a constant, derivative of a number is 0, so you have to account for the possibility that your original function, your antiderivative, had some sort of constant. And anti-differentiating this side, notice this is an infinite polynomial, and we can just integrate or anti-differentiate term by term. The antiderivative of 1 is just going to be x. The antiderivative of negative x squared is going to be negative 1/3 x cubed, as we all know. And then we have plus 1/5 x to the 5th power, anti-differentiating this guy, minus 1/7 x to the 7th power. We can guess the next one is going to be plus 1/9 x to the 9th power. Hopefully at this stage you can guess what the next one's going to be. Notice we're picking up odd numbers. And also notice that this is flip-flopping between positive and negative. We see patterns like this as mathematicians all the time. The next one's indeed going to be 1 over 11 times x to the 11th power, and this will continue. Plugging in 0, I'll do this quickly. This implies that c must be 0 as well. So really what we have is that the arctangent of x is equal to this series. So that's going to be x minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7 x to the 7th plus 1/9 x to the 9th power minus 1 over 11th x to the 11th, and that continues. And then what we can do is let x equal 1. And then we just wonder what's going to happen with this series. Well, we'll have tangent inverse of 1 is equal to 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1 over 11. And you can guess what the next one's going to be. It's going to be a plus, and that's going to continue. But wait a second, you guys. The tangent inverse of 1 is simply going to be pi fourths. Certainly well known at the time, and therefore we have pi over 4 is equal to, so pi over 4 is equal to this infinite series. And if we want to get pi by itself, if we want a series representation of pi, all we have to do is multiply both sides by 4, giving us this Gregorian series that pi is precisely equal to 4 times the infinite series 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1 over 11 plus 1 over 13 minus 1 over 15, and yada, yada, yada. This is the big Gregorian result. It's what he's most well known for. Well, I mean, and his telescope. I don't want to limit him to this discovery, but this is certainly a famous result from James Gregory. Going back to his results, almost spoiled our second historian. So that was kind of the arctangent series, and sort of we call it the Gregory series because it came before the big results of calculus. He was able to come up with this series representation of pi. But his brain, here's like some of his works that he famously published. He has a little bit of a tragic story because he died in his mid-30s. some say, or legend has it, he was looking through his famous telescope and he made some sort of staggering discovery, and it excited him so much that he had a stroke and he died. We know he had a stroke, and we know he was always looking through his telescope, but that's a little bit of a romanticized version of how James Gregory died. So questions pop up like, what did he discover? That's a great question. And also a question pops up of, what else could this guy have done had he had another 20 years of his discoveries? Prolific mathematician. We owe a lot to him. He came about 20 years before our famous Isaac Newton. But if he came up with a serious representation for pi a little bit less than a century later, a new mathematician made a new result about pi. So let's learn about this guy named Johann Heinrich Lambert. I always think this portrait of him is hilarious. I really think the artist here did him wrong. That just looks so menacing. He's not as menacing or hard to look at as this profile suggests. But anyways, Johann Lambert was born in he was known, and he had all of his work throughout the 18th century here. He was born in Mulhouse, Switzerland, which was a huge part of the Swiss culture at the time. I'm missing in parentheses. He worked in analysis, geometry, astronomy, and hyperbolic functions. This guy was wildly curious. He was very happy to study pretty much whatever the heck he wanted. And he was born an apprentice of a tailor, which was huge at the time. But his real passion was with the sciences and the mathematics. Actually, his passion was wherever his brain led him to. He wouldn't stop being curious about the world around him. He reshaped the mathematical world with his discoveries. He was a little bit he came a little bit after the famous Leonhard Euler, but they were pretty much contemporaries. I don't know how well they knew each other or anything like this, but at the same time, Euler was making all of his prolific discoveries. Alongside him, Johann Lambert was doing the same thing. As I said, James Gregory sort of passed the baton of pi to Lambert here. If Gregory came up with an infinite series representation for pi, Lambert proved that pi was an irrational number. In fact, he was the first to do so. So what Lambert proved was that pi, this number here, cannot be expressed as a fraction. And that proof is a lot more extravagant than the quick series proof that I gave you alongside Gregory's discoveries. So we're not going to do it in this video, but it was spurred by some of Euler's discoveries that the tangent, again, is relating back to tangent. The tangent function can be expressed as a continued fraction. Euler famously discovered that, and Johann here said, I wonder if I can prove that pi is not a fraction using what Euler discovered. And he kind of just developed Euler's findings. He worked in analysis, geometry, astronomy, and the big important thing for Lambert in this week's videos is he developed these things called the hyperbolic functions. He said there's these amazing relationships between the exponential and the logarithm, things like this. And he developed sort of a calculus upon their backs. And he realized that if we wanted to find the area under the curve of certain infamous rational functions, what we need to employ are these things called the hyperbolic functions, or what we should employ are these things called the hyperbolic functions. And once he started discovering things about the hyperbolic functions, really the results just kept coming through. Lambert was very giddy and very happy about what he was discovering with his hyperbolic functions. Here's some of his actual writings here, by the way. I always like seeing or trying to discover or find some of their official writings. And here's the title page of one of his famous books. But why is he important for this week in our class? It's the hyperbolic functions. This week's final two videos will be involved with the hyperbolic functions, and we'll sort of see a little bit of a development, we'll redo what Lambert did. And then pertinent to our class is these guys are wildly helpful when it comes to methods of integration and things like this. Famous mathematician, largely self-taught, wildly curious. I respect him for that. I am also wildly curious, as I hope you guys are as well. This world around us has impossibly many discoveries, or impossibly many secrets waiting to be discovered. And Lambert saw that, and he would not stop trying to dig up these discoveries. The big one being the hyperbolic functions. He extended the analytic framework of calculus by developing these functions and uncovering their deep relationship with logarithms. These functions arise normally, like I said, when we are trying to find the area under the curve of certain rational functions. His work shows how area can give rise to entirely new classes of functions, completing the transition from geometric intuition to sort of analytic structure. So Lambert is involved with hyperbolic functions, whereas, let me put them both in the same frame, our guy here, James Gregory, paved a lot of the road for calculus to develop, in particular in finding areas, and that's what this week is about.